Good morning. Yeah, the chorus. The chorus. Oh, one? Yeah, it does. It just go vibe. What the bit, yeah, it's so bright. Yeah. It could be 70s, 80s. It is kind of like Marmalade. Yeah. It is like Lady Marmalade, is that what you said? Yeah. Yeah.
She was bad, like. Yes, true. But they were not exist. They were not doing that. Yeah. I went up fail. Lift every voice and sit. All right, scoop. It's scaled. It's totally tall. Does my inside feeling fine? Like I'm so serious. See, also like it's on the computer. Yeah, that's like kidding. I don't think they would. They would not even. I'm so embarrassing. You like what? Okay, you're like. Sorry, what did you? I don't know. It was not. I don't know why you. I didn't realize. I didn't drop the like 15.
What's that? This is Anastasia. Yeah, one hit. One hit.
Yeah, they give me a little. Yeah.
Thank you, folks. Okay, folks, let's get started. Quick warm up. Let's get started. And good morning. I think just a question about how you would do something in particular. If I want you to find, excuse me, I want you to find 23% of 81. Would you just kind of Discuss with your neighbor how you would do this. Okay. I just want to know the method you'd be using. Chloe, can you tell us what you're doing? How do you find 23% of 81? 81 times 0.23. Do we agree that this will give us 23% of 81? Like, we do this in your head? Yeah, me neither. To estimate it though, you could estimate 20% of 83. Would that be difficult to do? How do you estimate 20% of something? Divide by 5, that's one way. It's another way. Multiply by 2 over 10. Oh, nice. Yeah. Any other ways to estimate 20%? Or to calculate 20%? So we could estimate something like 23%. We can find 10% and then double it. I'll do the same thing. But another way to find 23% of 81, does anyone do it a different way? There are other ways to do it. 23 out of 100 equals what out of 81? And did you ever see it done like this? Kind of as proportion. And they get the exact same thing. This is what we're going to be focusing on today when we're doing this thing. But I just want to make sure we're all on the same page for that. So, Chloe, thank you. So back to the packet. So that number 2 kind of snuck into your assignment last night. And you already know about this, but there is another irrational number. We've already been talking about pi before, but another irrational number symbolized by the letter E appears as a base in many applied exponential functions. This is defined as a value that quantity approaches as n gets larger and larger. It's also known as that. This is a German name. Does anyone have any sort of German experience? Would you know how to say like German language experience? How would you say that? Do you know? Nice. All right, so many of you probably in your head said something like Euler, but no, oil, and it's not even Euler. It's Euler. I think you said Eula. Is that right? Eula. Kind of like not a hard American R. Euler. But I would say Euler just because I'm going to respect the vowels and I have a hard time with the consonants. But Euler's constant at constants definitely not Euler's constant. It's also known as a natural base. I think that's what it had in your homework. And we'll talk about that a little bit today. The only thing you really have to know about E is that's approximately equal to 2.72. And if you remember 2.7, I'm quite happy. What you have to know about that is that 2.7 is between 2 and 3. You can hold on to that closer to the 3. Cool. Okay, so take a look at the blue graph, take a look at the red graph. Do you notice what they are? Discuss anything for what's the blue graph? What's the red graph? So blue is y equals, is it exactly to the x? Is that what we're seeing? Or apparently to the x? Yeah, we see this telltale point there, that 1, 2, and then 2, 4 is very clearly written there. 2 to the x, and the red one is 3 to the x. Both exponential functions going through that special point, 0, 1. So if we're graphing what f of x equals e to the x, we know that e is between 2 and 3, closer to 3. The point I'm going to label here, do you see where it is? 1, let's see, maybe there. Does that seem about right? And I'll say that's 1, e. I don't want to be exact. And we know that's approximately 1, 2.72. And we also know that this point is, right, this point 0, 1 is on that graph. So I could kind of follow that up here. So it's in between these two. Everything else is just approximated. I'm not going to ask you to find out what e squared is. But we could approximate it here, can't we? It looks like e squared might be about 6. Can you check what, do you see the E button on the calculator? What is E squared? 7 point, okay, I gotta adjust mine a little bit, 7.39. I have to go a little bit steeper. So like, I can go through there. You should all be able to find E on your calculator. Thank you. And on the left, it's gonna squeeze in between the two. It's difficult to see here, but, and I don't actually care what those values are, just that it's approaching the X in X axis. And this one is y equals e to the x. Okay, so this function, if you were to plug in a 1 to this function, you see that you get 2. That's pretty clear. And so when you plug in a 1, you get 2. When you plug in a 2, you get, I think you can calculate that pretty easily. 1 plus 1/2 squared. What does that equal? Without your calculator, I think you could do it. Let's see, this is 1.5 squared, and that is 2.25. Does that appear to match what's on here? I'm not going to have you plug in 3. If I do on it, you just kind of follow this along. And that's what happens is you plug in numbers that are bigger and bigger and bigger. They don't grow forever, do they? In fact, they approach a specific number. These numbers approach the number, and this is kind of like an asymptote here. This is going to be difficult to draw, but approach the number E. And that is the definition of E. This is y equals E. And what do we know about E? About 2.7. That's really all you need to know. Okay, so when we're drawing these graphs of the functions, we're going to use transformations, please. So does this seem right? Y to the E? Y equals E to the X? Does that look about right to you? You see the 2.7-ish? Cool. So transformations. Let me try an A. I'll call on someone to see what they did. Check in with your neighbor. Maybe Haley, don't forget you got Katie behind you, so it's the three of you today. Did you get something? Appends, yeah. Is that what you mean? Appends. I'm gonna ask you in gestures. It looks like you need a little bit more time. Okay, would you please show me what this two does to the parent function? Oh, don't hurt yourself. Yeah, it is a vertical stretch. This two moves it two to the right, and this one moves it up. Exactly. So, at least could you help me with this one, please? Is your hand okay? Okay.
So, move it over forward and watch everything for it happen. Two first, so
Okay.
it was estimated for -1 point less than, it would come up with that with 0.3, something like that.
Okay.
So moved it there, and then, but I moved it over first, right?
Okay, so maybe I'll do this in different colors. So you multiply them first. So maybe like right there.
You know, for about 5.4.
Okay. Does that make sense, everybody? That vertical stretch by factor of two should just multiply all these y values. Kind of visually, didn't you? Especially the one on the left, by two. Okay.
All the things that come out. Two and have one, so just add it at one, two, at one.
Nice. Okay, so like that leftmost point went here and then here, like there-ish. Does that seem about right? And then this one to the right two and up one, to the right two and up one. Okay,
And then I think that
nice. What line is this called? The asymptote. Thank you. Does this make sense? Does it look like a W? If it did, there's a problem. It should make a nice smooth curve. Thank you, Elise. Just kind of follow it up and make sure you are adhering to the restrictions of that asymptote. And thank you for saying the equation of it, y equals 1. Yeah. Okay. For B, please discuss the transformations before you do anything.
that way one, that way one. And
At least thank you, by the way. I forgot to thank you. Can you show me which direction that one is moving the graph, please? That one is moving it to the left. Are we good with that? Why not the right? We all factor out that negative. Oh, so it's the left? Is it left? Hmm. Be careful. One, two, right. Pardon? You start with the reflection. Anything that's multiplication based comes first. Are we ready? Sam's ready. He's been ready. Ella's ready. Ella's been ready too. Okay. Ella, you were actually told. So can you help us with this one, please? Okay. Okay. 2,8. I think it is 7.39, isn't that what we were told today? But let's do it. That's not like some weird point. Okay. Okay. So I'd like to hear. Okay. On the 5. Oh, they're choosing all these really interesting points. Okay. Okay. Yeah, it works when you're doing this visually. It's fine. Okay. At 3? Oh, okay. Y equals 3. Okay, so right like there. Exactly not 3 I was thinking of, but it works. Yeah, it works. It's fine. Yeah, okay. Okay. And I imagine that you also dealt with 0, 1. It just kind of stays there. It does, it just chills right there. Yeah, then all these do what? Okay, 1 to the right and 2 down. So I'll go ahead and do this red again. 1 to the right and 2. You're, you're ahead of me here. No, I appreciate your speed. And what line did you call it? What is it? Okay, and that's at y equals -2. Thank you. This kind of comes up like this. Are we good? Let's check to make sure that we actually moves it the correct correctly horizontally. What point should I check? Why are you these crazy points? I care about 3 points. For the original graph, I care about this one, and this one. So I'm gonna go to, yeah, they're kind of lost in the obscurity of what's going on here. I'll go ahead and check what happens when you plug in x equals 1. What happens to this function when you plug in x equals 1? Yeah, what? -1, isn't it? E to the 0 is 1, 1 minus 2 is -1. So that does work. If we would have moved another way, there wouldn't have been a point right there. So we nailed it. We got it. Fine. Ella, thank you for your help. And thank you for showing us a different way of thinking about this. Any questions? No, seriously, it's interesting how you took different points and it was fine because it's all done visually anyway. Insatiable killer. Dun dun dun. I need some background music for that one. It's a reputation that the gray wolf acquired in the United States in the 19th and early 20th centuries. Although the label was undeserved, an estimated 2 million wolves were shot, trapped, or poisoned. By 1960, the population was reduced to 800 wolves, from 2 million down to 800. The figure at right shows the rebounding population in 2 recovery areas after the gray wolf was declared an endangered species and received federal protection. So it looks like it was protected in the Northern Rockies and the Western Great Lakes. Can I answer any questions? Here, you guys okay? Okay. So there are there's an exponential function for the, let's see, the exponential function f of x equals blah, models the gray wolf population in the Western Great Lakes, f of x, on the x years after 1978. Okay, according to the model, what was the gray wolf population rounded to the nearest whole number of the Western Great Lakes in 2018? Okay, so if we're using this, so it is f of what? F of what? F of 40, are we good with that? After 1978, how long did it take to get to 2018? It takes 40 years. So we have 1144 e to the 0 point. Right. According to the model, well, it says the function models the gray wolf population. Because I think the bar graphs are like the actual. Right? The bar graphs that we see here, these are actual numbers. But math is meant to model what's happening in reality so it can make predictions about what happened in the past, what's going to happen in the future. So it's not exactly right. And it's trying to get a model for it, but it's not like law obey exact. What's that? The model is not the graph. It's saying here that the function models the gray wolf population. So it's not like an exact, what's exact is whoever counted the wolves. That one is exact. But you can see that here it is kind of following exponential growth. Here, also exponential growth, at least I think there. Yeah, great question. Why not just 2 or 3 or something, right? It's a very, very common number to use anytime something is growing, especially population. And we'll talk more about that. So right now it's something to get used to. And I'll give you a little bit more insight a little bit later today. Yeah. Oh, not today, but yeah, next year. You're right, it can't just grow exponentially forever. But yeah, this is a mathematical model. It's not the law of the wolves aren't saying, oops, we had too many babies because the model said so. This is just a way to approximate. So you have a calculator. If you could please type this in, I'd appreciate it. Because I do not have one. Oh, 325. Oh, thank you. I miswrote the model. Nice, good catch. Do we agree with this? Again, saying the same thing? Okay, so Western Great Lakes, how does that compare to reality? Well, pretty close. Pretty close. That's it. And I don't think that could be 0.675 wolves, so I'm gonna just round that to, I'll cut it down to 7. Approximately that many wolves. Does the model underestimate or overestimate the gray wolf population of the Western Great Lakes in 2018? Underestimates by, was that 25? You can round up if you want to, or round down. For something like this, I'm open to either one. But if you left it at 0.6 wolves, I'd be a little bit concerned. Okay, are we good? Was there a question I can answer about the graphs or anything we've done so far? Yes. 25. Oh, I just did the actual. This is what they counted. That's 42, 22. And then I subtracted 41.97. Thank you. Any other questions? Yeah, please. Well, this is estimation. The model is just a way for mathematicians to say, this is what appears to be happening to it. We can see what's going to happen in 2030. So the scientists would probably tag, whoa, are actually counting this model. But this is what we're saying. So they can do it. Come from that. Compound interest. You studied compound interest, haven't you? I'll give you a moment to work through example 1. You can discuss it with your neighbor if you like. Year 1. Oh, 1 point. 1.6. Yeah. You want this to increase. You want to have the amount you started with plus the 6%. Is that clear? And that gives you $1,060, I think. is $1,060. Okay. That's after 1 year. So they give you $60 for keeping with them. So does that mean every year you get $60? Now, what kind of interest is that called? It's called simple interest. Doesn't exist. Okay. Maybe that's two friends. Okay, so the next year, take the previous years. Something we have to do. Five. Six. Oh, points. What's that? That's what okay, and for year three, we have the previous year times 1.06. I'm going to abbreviate that as 1.06 to the third power. Of course, you can just take this one and that by 1.06. At 1.06. And then the last one is what's the final amount? If you want to go directly there, you can say, well, I started with 1,000, 1.06 to the fourth. That'll get you that. So you don't have to do every single year. You can go directly to it. If we want to know the 10th year, just put it to the power of 10. Okay, so we are going to kind of generalize that. If you invested P, and P stands for? P stands for in general, when finance, talking about finance. No, price, it's a good choice. Principal, does that sound familiar? Principal is the amount of money you start. So year zero, we have plus ER or plus R. So plus R. Year two, plus, sorry. R is the rate. Thank you. So P is principal. Well, R is rate. And rate is always written as, yeah, that's it. One, you said that a little bit, or maybe in another class. Most savings institutions have plans in which interest is paid more than once a year. It's not like they wait till the end of the year and say, here's your X% or R%. Compound interest is paid twice a year. The compounding period is 6 months. We say this interest is compounded. Period is said to be compounded. Some plans allow for monthly compounding. In general, compound interest is paid n times a year. There are n compounding periods per year. So if a bank gives you 4% per year and they compound it semi-annually, does that mean you get 4% and then 4% again? No, that would be 8% yearly. So if it's semi-annually, that means the first 6 months you get 2%, and then the next 6 months you get another 2%. Or if it's quarterly, that means each 3 months you would get 1% for a total of 4% over the whole year. Opportunity to invest 1,000 to account. How much would you have after 4 years if it earns 6% compounded semi-annually? Okay, so what happens is we have, let's see. Yeah, I think I can go right to the formula first. Principal. That rate is going to be divided by the number of compoundings. Okay, let's go. $1,000 now. 1 plus 0.06. Semi-annually, how many times you get that interest? If it's 4 years, and it's over the 4 years, you're going to have it a total of 8 times. So that's 4 times. This number will always be. Notice how this compares to if we just compounded annually. 1262, 1264. See your benefits that have a little bit more. Any questions? Try example 3. Got it? Yeah. Results. I have a name. I'll be calling in just a few seconds. Mackenzie, can you tell us what you typed in your calculator for this one?
And then like in prices, you have one price, your taxes, your, and then the power, 4 times.
Are we good with this? Does that 4 times 52 make sense? It's 4 years, but you're getting a little bit interest every single week. So it's got to be compounded like that. And what's the number that resulted? Okay. So, and let's see how that compares to the other ones. Did you all get that same thing? Nice. So it's creeping up a little bit, little, every time we increase the number of compounding. So what is the limit? How often can we compound interest? Multiple times a day, like maybe once an hour? Once a second? Once a millisecond? So some banks use continuous compounding, which means it's compounded every instant, like like yeah, every always. Like, how do you even quantify that? What's the year being divided by? Infinity, isn't it? If it's continuously compounded, where the number of compounding periods increases infinitely such that it is compounded every instant. Okay, so go ahead and put your pencils down for a minute. Let's take a look at this situation. Just watch me now. A equals B times 1 plus R over, I can't put infinity, but I'm going to put N here. And again, just pencils down. You're not accountable for this. You're just accountable for what comes out in the end. I'm going to have a little bit of algebraic fun here. I'm going to make this A equals P times 1 plus 1 over N over R. Do we agree that's the same thing? And then let's see, how can I make an N over R here? T times N over R times R. Does that give me the same thing that I started with? Yeah, but this is the same thing. Okay. And it move things around a little bit here. Over N over R. And this is a little bit messy, and I apologize for that. B times R. Okay, this. Now what's happening is that N is increasing to infinity. So this quantity is increasing to infinity. Let's go with quantity a bit. Does that look familiar at all? Right, if this is going to infinity and this is going to infinity, what results? Let's think back. Think back to what we did earlier today. And look at that. Isn't this going to infinity? And this was going to infinity too? And that by definition is Euler's constant. So I'm going to replace that with E. So this is P times E to the RT. And this is the formula that you need to memorize. You don't have to memorize the process, but A equals P times E to the RT is continuously compounded interest. So you have to do the process, 0. Yeah, like for a test or quiz, 0. 0, for sure. That's why I said put your pencils down, don't worry about it. This is all you need to have in your notes. A equals P times E to the RT. That's all you need to know. And it's really a beautiful formula. It's really, really nice. And so you can see E comes from natural growth. If it's continuously compounded, and it applies to populations and interest. And there are other applications too. So example 4. Actually, let's, instead of doing example 4, let's say, what about if you have $1,000 and you compound continuously for 4 years at an annual rate of 6%? So we can compare it to what we had before. Does that make sense to try that now? Did you compound it semi-annually, weekly? Let's see, continuously. So A equals 1,000 e to the 0.06 times 4. What do we get there? I'm guessing a little bit more than 1271. So we have 1271.25. Oh, are we good? Did anyone else get that? It will be my calculator. Notice it is a tiny bit better than weekly. It's not much better, but you can imagine if you're dealing with $1 million investment, it would be significant. Or more than $1 million investment. So yeah, continuous compounding is as good as we can do. Go ahead and try example 4. Example 4, both parts, please. This first one. The heads. What did the rest of you do? Just kind of weird. For continue for the next part, Tyson can't help us. Haley R. So I can't take 5,000 times. over 12, okay. What times what? 10 times 12. I hope that makes sense, everyone. 10 times 12. 10 years, it's being compounded monthly, so that's gonna be 120 times. And did you get a figure for that in the end? 7,000.96. Do we agree with this? Nice. And I think there's a second part of this. Oh, how much more is this if it were to, okay. $6.60. Are we good? Answer any questions? Grab your questions. Can we take a short break? Sorry, I'll answer this. The time is now 52. We will resume at 52.
Wait, all right. I sent the original because I didn't know any other things and it was so hard. Really hard. You gave a speech about that.
You gotta finish up your conversation. And head back to your seats, please. Yeah. Okay. Let's finish this up. We just have two more problems to do. I hope it makes sense that this is an exponential problem. Anytime the variable is an exponent, it's an exponential equation or problem. This is one type. So if 2 to the x equals 3, what is 4 to the negative x equal? So I know as algebra students, you might be inclined to solve for x, but we're not going to do that. Instead, what we're going to do is manipulate the first equation such that It looks like that other one. So when I have 2 to the x equals 3, how can I make that 2 into a 4? Is that even possible? Would multiplying by something do it? Or multiply by 2, would that do it? That'd become 2 to the x plus 1. So how about if we square both sides? What is this equal to? The left side. That is 4 to the x equals 9. And if I'm trying to make it 4 to the negative x, then I'm going to raise both sides to the negative first part. Yeah, 4 to the negative x equals. What is 9 to? Would you just check it with your neighbor? What is no calculators here? What does 9 to negative 1 even mean? 9 to negative 1. Joanna, what does it mean? Are we good with that? You're good? That's exactly what I was looking for. Thank you. Katie. Oh, like why is this equal to this? Is that what you're asking? Ooh, good question. Um, I will address that directly to you right after we finish this assignment or the lesson here. Any other questions? Yes, Charlotte. Well, the question's asking 4 to negative x equals what? But you're right, we could apply this. We could say that this is 1 over 4 to the x just by definition negative exponents. That's not asking for that. It's asking for an expression that's equal to. So 9 to the negative 1 is a good one, but I would expect you to say that. Chloe. Well, good question. Thank you. Let's say we had 2 times 2 to the third power. Is that the same thing as saying 4 to the third power? Right. So the exponents have to come first. So we could do something like 2 to the 3 plus 1. We could do that because they have the same bases. But if we did that, and it's so tempting to do that, if we start with this and multiply by 2, then we get 2 to the x plus 1, and that doesn't take us closer to our goal. Oh, I'd have to multiply both sides by 2, wouldn't I? Now we're trying to figure out 4. Great questions. Thank you. Any other questions? Katie. That is nice efficiency. Yeah. Yeah. Why not just get to the answer? Perfect. Yeah, that's a really good idea. Any other questions? Okay, find the exponential function with horizontal asymptote y equals -3, whose graph contains these points. What do you think we should do first? Did someone say cry? Okay, after crying. Yeah, draw it, right? Draw it. Oh. I love that. I'm hearing -3. Does that make sense? We're going to see a -3 in the end. We knew it, it used to be at y equals 0, and that's y equals -3. So it goes coming down. I'm going to do the 2 points, y comma 0, comma -2, and -2, comma 1. Does this have a stretch? Is there a vertical stretch on here? Because I'm seeing this. They gave us that. Isn't there always that 1 in between that asymptote and that 0, comma 1? I'm seeing no vertical stretch. So how do we do this? I'll give you a minute. So how are we doing this? You're not doing guess and check, are you?
Yeah, we use it. Right.
Okay, so we know what this looks like. I'm going to talk you through, there are different ways to do this. I'm going to talk you through how I would do it. We know it's exponential, so I'm going to make this y equals b to the x. Oh, yes. And we also know that it has a vertical shift. So I'm going to put a -3. Did you start with this? Really, all I have to do is figure out the b. How do I do that? We have a couple points. We plug them in. I see. Oh, we are going to log here, right? Really, all we have to do is plug in one of the points. Now you notice we plug in 0, -2. We plug this in. I don't think it's going to do anything. -2 equals b to the 0 minus 3. Do you see that this doesn't tell us any information? It just tells -2 equals -2. Tells us we're on the right track. It doesn't give us any good information. And this is because there's been no vertical stretch that it's just said we're good with this. So instead of plugging the other one, I'll go ahead and plug in 1, -2. So 1 goes here. B to -2 minus 3. 4 equals b to -2nd power. So how do I solve for b? Salud. How do I solve for b? I'll raise both sides to the -1/2. Does that make sense? If that would solve for b? Just using algebra. So b equals, what is 4 to the -1/2? Just check with, no calculators, come on. 4 to the -1/2, check it with your calculator, not your calculator, your neighbor, what is 4 to the -1/2? Maybe could you help us out with that 4 to the -1/2? How do we do that? Nice. Does that make sense? I think we could. We know the square root of 4. I hope. 1/2. Yes? Thank you. So our equation is y equals 1/2. to the x minus 3. Yes. Oh, is this the same thing as saying 2 to the negative x? Is this true? Either one is fine. So we can see it as a reflection of something that's growing into something that's decaying. Or start with it as it's exponential, and then we see, oh, that base is 1/2. That's how we know that it is a exponential decay function. They both do work. Yeah, for those of you who start with that negative x, I love it. If you did that y equals b to negative x minus 3, that should get you that b equals 2. Yes, Katie? Where did it go for the negative 1? 4 to the negative 1/2. So that's equal to 1 over 4 to the 1/2 by definition, negative exponent. And 4 to the 1/2 is 2. You have a few minutes to take a look at your assignment. Nicely done today. Today was packed. That was a lot of information. Well done, folks.